Hello, good morning, everybody. I just asked somebody to let me know, give me a
Good morning.
signal if you can all hear me.
Yes, we can hear you.
Morning, yes.
Gentlemen, ladies, hello, this is Dimitrios Vasco speaking. This is to let you know that, actually to introduce to you, Dr. Olga Ktenido. She's coming from the National Observatory of Athens, and she's going to be our resident expert on the ground motion amplification, ground motion and soil stuff, anything with soil and
Dimitrios?
seismology. Olga,
Oh,
it's your call.
I'm afraid I can't hear a thing. Not good. Okay, good. Yeah, okay, so it seems that you can all hear me, but I can't hear you, which is not at all great. Not great.
Well, gentlemen, ladies.
Okay, so this is embarrassing. Thank you for introducing me. I'll be keeping my eye on the chat and I'll try and sort this out during the first break. So I guess I'll get started and hopefully I'll be able to receive some sound after our first break. So I'll start sharing my screen. Great. So this is going to be a lonely first 1 hour. So welcome everybody and good morning. My name is Olga Ktenido. I'm a researcher at the National Observatory here in Athens. A beautiful place opposite the Acropolis, actually, if anybody wants to visit. So I'm an engineering seismologist, and I'll be talking to you for this lecture and the next one about the effect of local geology and soil formations with respect to what that might do to your beautiful usual assumptions of rock or let's say a typical soil of 400 as I think you're taking for your semester exam. So first of all, it's nice to meet you. And just to give you a bit of background about myself, I'm from wonderful Thessaloniki, Greece. And I've studied and worked in a few places around the world before coming back home a couple of 3 years ago. And aside from earthquakes, I love cats. So if anybody wants to see more about my kind of research, you can see it here. And actually, you can do that for any of the teachers you have and you're interested in. So ResearchGate is basically a kind of academic Facebook, let's say. You can have a look at what folks do. And you can also connect with me on LinkedIn if you would like to. And actually, even though it's not at all the topic of our lecture today, I would very much like to encourage everybody who doesn't happen to have a LinkedIn account yet to do so. You're soon going to be finishing your master's, and to start hitting the job market, it's probably one of the #1 things you need to be doing. So thinking ahead. So why do we care about soil, which is basically, which is basically why we're here today. A really nice explanation I found over the years is that everything needs to be supported by soil or rock. And if it isn't, it should either be able to fly, float, or otherwise it's gonna fall over. So that convinced me pretty well when I read that. And because I happened to witness a pretty striking soil effect a few years ago in my life, I wanted to share a couple of pictures with you just to make sure you're really convinced about the role of soil, although I'm sure you are from your soil mechanics courses. I'm guessing you guys are all civil engineers. If you're not, and by the way, if anything during this course is not making sense, or if you have questions, or if you would like something repeated, please feel free to text me. Right now, I'm afraid if you open your mic, I can't hear you, but do text me and I'll try and keep an eye out on the text box at most times. So in September 2017, there was a major earthquake in Mexico City, the capital of Mexico. And these photos are from a building we visited, which of course is no longer inhabited and is probably demolished by now. So this was a multi-story building. You can see how the foundation failed from the soil failure around here. Hopefully you can see my cursor as well. And we're walking up the staircase, and this was actually made up of two buildings, like two L's back to back. And reaching the 6th floor, you can see the separation and the stairwell and between the two buildings. 9th floor, you kind of need to jump to going up the stairs. 14th floor, we didn't get further than that. This is like a meter's worth of opening between the buildings. So nothing else was wrong, just the underlying soil was not able to take the earthquake. So hoping that one of these things might have struck a chord with you guys, I've put here a couple, well, not a couple, around a dozen keywords I wanted you to have a look at. And if any of these don't ring any bells at all, then do feel free to flag this up in the chat box. So we're going to be talking about site classifications. We'll be talking about the Eurocode mostly, with a very tiny mention of the American code. We'll be mentioning shear wave velocity, soil damping. We'll be talking this time and mostly next time about spectra. So response spectra and Fourier spectra are the two main kinds of spectra we'll be mentioning. So the pseudo acceleration, PSA, peak ground acceleration, resonance in terms of soil columns and in terms of structures, earthquake magnitude and different measures of intensity and the difference therein. So I'm not seeing anything in the chat. So hopefully they've all rung a bell. Even if they haven't, we'll be going through them in some detail in these two courses. So I thought I would give you a bit of a heads up on some of the contents we'll be going through. So we'll start by having a look at site classification according to seismic design codes, a little bit about strong ground motion parameters, and I'll just note here that because there's a bunch of you guys coming from different places and likely not exactly the same background, although I am assuming you're kind of into the main civil engineering concepts, I'm not assuming too much about the seismology background you might have taken in your undergrad studies. So there might be a few things that some of you may know well and some of you may not. This is also a little bit about trying to catch up and reach a common, let's say, page. So we'll be talking about soil resonance and building resonance, site response in general. the simplified 1D effects and what might change because of base and edge effects or topography. We'll be looking, this is going to be next time, at theoretical and empirical methods to quantify the effect of soil. And when I say the effect of soil, I mean very often you might assume that you're computing ground motion on rock. You have your scenarios, you do your PSHA, and you assume that you're computing spectra or whatever on rock. As you might have seen walking around, well, anywhere in the world, usually there's a little bit more on top of rock. And usually if you live in a city, most cities in the world were developed around where water was not too scarce and where folks might be able to, let's say, cultivate the earth. So very often, well-populated places around the world are actually built on soil sediments, and basically this kind of increases the seismic hazard for most highly populated places in the world. And this is why we need to know what kind of things to expect when we have additional sediments on top of our assumed bedrock. So spectra, we talked about those, Fourier response, and of course design spectra, a lot of which you have seen until now, I'm sure. And given time, we'll have a quick look at dynamic soil properties and a little bit about nonlinearity and liquefaction, if we manage to sneak that in at the end of next week's class. So starting with side classes. And by the way, I won't be asking you all the time to ask me questions because I can't hear you, but please feel free to just step in and interrupt me in the chat box if you need to. So this is Carl Terzaghi, and anybody who's done soil mechanics should definitely know him. He was an awesomely cool guy. I've copy pasted one of his very nice quotes about soils, and because a lot of you probably may know even a lot more about steel or concrete, he makes a nice distinction here. So Terzaghi says, unfortunately, soils are made by nature and not by man, which is something we may not necessarily have thought of when we think about properties and, for example, structural materials and properties of soil on which we need to found our superstructure, basically. So products of nature are always complex, unlike those of man, which we try to fit into ISO and all those kinds of rules. So as soon as we pass from steel and concrete to earth, the omnipotence of theory ceases to exist. Natural soil is never uniform. Its properties change, and we need to always be aware of that. We'll have a couple of slides on it, but we need to be aware that its properties change from point to point, while our knowledge of its properties are limited to those few points where we took our samples from, if we did that, or where we happened to do our non-intrusive field surveys. But in any case, we only know what's beneath us at a few precious points. So basically, this means that in soil mechanics, and also, of course, in soil dynamics and in seismic and dynamic soil properties, the accuracy of computed results never exceeds that of a crude estimate. What does this mean, among other things, for you folks? If you ever write a report and you give, for example, soil properties, let's assume, at an incredible accuracy of 2 decimal points, for example, the shear wave velocity of this profile is 211.31 meters per second, you're going to look like an idiot because everybody knows that that kind of accuracy is fake and that we can never hope or dream or wish to have that kind of accurate knowledge. which means what? We need to be able to grasp the bigger picture, and we need to be able to understand at least the basic theory and the basic physical mechanisms and phenomena, because we'll never be able to have any very, very painfully precise estimates of anything. So coming into the effect of soil, I wanted to try and have a little quiz. So you can use your computers or your cell phones, and you can log into kahoot.it. And I'm going to give you a pin to try and do a quick little quiz. Let's see if this works. It's an awful lot slower than last night when I checked it without the Cisco. But here you go. If you want to punch in 409-6860 and just give yourself a nickname, and I'll see why this generates the list of players. And since I don't really know you guys, this is gonna be all new to me. You don't need to be shy, by the way. I'm not gonna be grading you on this. This is just to get us going. Dimitri, did you also join? Okay, I'll start loading the first question. Dimitris is also in. We'll never know if he tries to rig it a little bit. So, a clay and a sand have different. You can give me as many answers as you wish. So you can see your question and your possible answers here. And on the device of your choice, you can choose which of these you think are correct. And the timer here gives you a bit of time. So I upped it to 1 minute rather than the half I would have given because it's all kind of new to us. So clay and sand are both soils as opposed to rock. We can see the answers as they're piling in. Dare to answer, don't allow the time to run out. So we'll be looking at a few of these, and a few of these are pretty critical. So definitely grain dimensions. We'll be looking at the kinds of mechanisms nature has given them to cope with shear. Shear is what earthquake does to things. So densities we don't care so much about, and liquefaction, yeah, it can be different. So most of you knew about the grain dimensions, and less of you knew about the liquefaction, which is as it should be, I think, based on the assumed background. Haha. I don't know how the scores can be so accurate, but okay, here you have your scores. Dark Magician doing pretty well. So I'll load the next question. So let's say you're sitting comfy in your house. Would you expect the shaking of an earthquake that happened near you to be stronger if your house were built on rock or soil? So this is about the amplitude. Stronger shaking or less? You have 10 more seconds. And I want you to have an opinion on this. Rushing in at the last minute. So a few of you would feel safer on rock. Most of the time they shouldn't. Of course, if you have a clear rationale for that, I'm open to hearing it because there is such a thing as a topographic amplification. If this rock were at the very top of a hill and you were unlucky enough to experience topographic amplification at the crest of a hill or of a ridge, you might not be too happy. But generally, the amplitude is stronger on soil, which is why we need to take this class. Okay, different faces this time. Now imagine you're in your lovely home. An earthquake happens not too far away from you, so you can feel it. Would the duration of the shaking be longer if you were on soil or rock, or would it not matter too much, do you think? A few more seconds. Everybody was really fast this time, very confident. Let's see. Okay, some people are sticking to their guns. This time I need to say that it is soil, really. It tends to amplify the duration, and we'll see a few plots of that. But if anybody has a clear rationale for the opposite, feel free to text it. Hera and Dark Magician again. And we've one last question. You can choose more than one. So the seismic design codes you all know and love, which of these do they take into account? The type of your geomaterial, so soil, rock, etc., the thickness of each layer in your profile, the total thickness of a more generic layer, for example, the sediments, or none of these, they don't care. You didn't try. I don't think I can replay it, but I wish I could. So this is going to give you the winner, but I really wanted more input on the last slide. Okay, so this is your winner, but it might have been a tiny bit rigged. So for sure, well done to Dark Magician and Jesus. So this was the last one, and only a few of you attempted it. But if you want to write anything in the chat and have another try, you can totally do that. Here you can actually see what really is taken into account. So you can actually see the cheat sheet, I'm afraid. So the codes care about the type of geomaterial and about generic things. So roughly, if you have more or less or no sediments, that's something they might care about. They're not as silly as to ignore the differences between soil and rock. So answer number 4 would have been wrong. They do care a little bit, but we're not there yet as to have very, very detailed stuff in our codes. And as you can imagine, the example I gave you, it says thickness of each individual layer. Well, we love to have that, and the tools we're gonna give you in this class will give you a few skills to estimate a lot of additional things, even with your own two hands and a pencil and a piece of paper, with respect to what the Eurocode does. So we're going to give you some more info on this. But in order to have a good profile and very detailed info about your soils, as you can well imagine, you need to pay some money. Because as we said, we can't really see what's underneath us, except at a few locations where we have samples or where we did field tests. And any of this costs a fair deal of money. So the Eurocode basically asks you, or any other code, I think, that considers soil asks you in these generic ways. So this was our little introductory quiz. If you did well, you can go ahead and feel happy. If you didn't, you can feel even more excited about learning the answers and the rationales behind them these 2 days that we're going to be together. So we're going to start with having a look at the Eurocode. And I need to move the little chat box a little bit. Sorry, it's lonely doing the class like this. I need to be checking the chat box and what I look like when I talk to you. So this is the very typical table from the Eurocode, and in terms of engineering seismology and let's say the soil part of Eurocode 8, if you leave knowing one thing, I suppose it should be this. As long as you understand its pros and cons at the end of these two classes. So the Eurocode basically gives you a table where it allows you to categorize any site you build on with respect on the geomaterials you have, and it gives you a few options for how to do it. So you have classes A, B, C, D, E, which are considered, well, A, B, C, D are pretty normal. E, I would say, is a bit unlucky. Maybe it's not too good. And you have two special cases, S1 and S2. And if you have those, you usually need to do additional checking. You can't really use the prefabricated, the predefined solutions that the Eurocode gives for the typical site classifications. So you see a bunch of columns and a bunch of numbers. You have your ground type, and first of all, you have a geological description. A, for of course, is the best thing you can have, which is rock or rock-like material. If you happened to be a geologist, you would know that very good rock is not to be found right at the surface where we build. So there's always a difference between rock, the way we engineers mean it, and the way a true geologist or seismologist might mean it. We're going to have a look at what all these things mean. So the first column that allows you to classify says VS30. Its units are meters per second. And short mental note, if you're ever unsure of anything, one of the first aid kits you can turn to is having a look at units. They very often lend you a helping hand in understanding what something is. So this is velocity. And do you all know what VS is? So not being sure, I'm giving you the most famous cartoon on the types of seismic waves. I very much hope you know about P and S waves. These first two types are what we call body waves. They're like the primary kinds of waves and the ones that arrive first. S waves are the ones you feel the most in an earthquake. So if you felt it, maybe you've had a little jump like this. This may have been the P waves. They're compressional, so like an accordion. They move kind of like this. And S waves are the shear waves, secondary because they arrive second, but they're the worst ones for us in terms of what structures feel and what the soil may fail under. Both of those may fail under shear, mostly, not compression. And they're the strongest thing you'll feel, which is kind of in the horizontal direction, usually. And then you have Rayleigh and Love waves, which are the surface waves generated mostly because of soil layers, and we're going to have a look at that. So Vs is the velocity at which these guys travel through our specific medium. So it's a property of the medium, of the kind of soil we have. But in order to classify not a soil, not a single point in the soil column, but to classify the entire soil column, so the site where we're hoping to build something, what we do is we use VS30. What VS30 is the averaged value in the first 30 meters. And guys, as they say, stop me if you've heard this and ask me to go faster if you've all heard of something. There's absolutely no reason to go slow or go through basics if all of your collective level is much higher. So I'm gonna need your feedback to kind of gauge, you know, how we're going in terms of pace. So this here is the equation that the Eurocode gives. So it's a time averaged mean VS. Here I'm giving you an example profile. This could be the VS profile as measured through geophysical surveys surface. And this might be a log of the soils you encounter. Maybe you might have that, for example, if you drill a borehole. And it's very often that boreholes used to be drilled or are often drilled down to 30 meters, which is why we invoke this 30-meter averaging. Around the world, most borehole data are to the order of 30 meters depth. So look at this guy here. So small velocity increasing with depth. This is what we expect. The velocity of the shear waves is very tightly connected to the shear stiffness. For example, the shear modulus of a material. You've heard of shear moduli before, I'm sure. For example, we call it G. And you just average that over the first 30 meters, but you don't just do this VS times this thickness plus this VS times this thickness, divided by 30. Rather, it's kind of the other way around, and you do 30 divided by, let's say, an average time. This thing here, distance to velocity, is time. So this is the way the Eurocode decides to do it. And if you try and do it both ways for a given profile, I'll give you a simplified one in a couple of slides, you can find the small difference that you get between the two methods. So this is another, stolen off the internet profile. We don't care where it is. We have our geological description out to the magic number of 30 meters depth. And somebody did some VS measurement that reached 20 meters. What you do if you don't have more than 20? You kind of assume the same. You kind of take the risk and assume it increased a little bit. That's why you're engineers. That's why they're going to pay you to do this. Because at some point you need to exercise some judgment. So here you have your little Eurocode 8 table. So how would you classify this without even doing the math? A rock has to have a VS over 30 meters. That's more than 800 meters per second. A B-type site, which is a pretty darn good site, would allow you several tens of meters of okay, well, kind of capable soil on top of rock. Fewer of not so capable soil. So a B site would be 360 to 800 meters per second. And the C site, which is not stiff but soft, would have deeper deposits, which are quite weaker and softer, so lower VS. So an average VS of 180 to 360. As you can imagine, the numbers are rather arbitrary, but we're used to these numbers now. So just look at this profile. Can you kind of gauge? Would you give it an A? I can't see an answer, but I'm very much hoping none of you is thinking yes. So we can't even see 800 here. We haven't reached it, not in a long shot. What is the other key number? 360. If you draw a vertical line here at 360, you might say you're mostly below it, right? So at the, at the drop of a hat, I would go for C, and then I would try and do some calcs, right? Now I've made an easy little profile for you guys, and I would like to encourage you to try and have a go at it and get a VS30. And you're free to use both the Eurocode version and the one you might have thought of just on your own, which would be, how do I average things? This, and I use the thickness as the, let's say, the weight, this plus that. What you do when you have bedrock and you haven't drilled past that, because if you hit bedrock, it's a pretty good sign that you can now stop drilling, right? What better do you expect? So here, what would be your preferred value? To make you do it, I'll give you a minute and a half, and I'll try and do it myself as well. Okay, Hamdi's made it easy on you guys, so you can agree or disagree. I found out my calculator's not working, so I'm gonna rely on you folks. Or this is gonna take too long. I think I'll just do it the old-fashioned way and show you the piece of paper like I would have done if we were happily in class with a whiteboard. So, what can you see? I think you can see this. So this would have been what one might have done if they did not have access to what the Eurocode gives you as a function. And this is what I hope at least Hamdi did, and he can confirm by text. So this is how you would have gone about it. This is very medieval for 2021, but I can't do better without my calculator. So you would grab 10 meters, 10 meters, and whatever you need from the last one, which is only 10 meters. You've reached 30, you're fine. And based on this, is this an A or B or a C site? Overall, so 473, which is basically 470 or a little less than, okay, great, a little less than 500. This is a very typical number for what we would call a stiff soil site. So it's not amazing. It's not like 600-700 where it's like really stiff, but it's okay-ish. you would not be flirting with the rock limit. So 700, you might say it's soft rock and, pull it downwards a little bit. But it's very decent and it's nowhere near being considered very soft because it's pretty much higher than the 360 limit. So close to 500, it's pretty okay. It's pretty in the middle of its class. So if you want to play around in your own time and change the numbers here and see how things change, be my guest. You can try and increase them a little bit to see how much you need to increase them before you can reach a class A, a rock, or what you're allowed to consider rock, which is 800 overall, which means you could have like 5 meters of something softish, but you would have to have rather competent guys for several meters. So we've seen what VS30 is and what ABC, etc. is. How indicative do you think is VS30? I could be standing on any kind of soul profile right now. How indicative would it be if I said it's a VS30 470, like Humpty found? How many other profiles in the world can you imagine that would yield this same number? This was one of them. I bet somebody can come up with an algorithm. I'm sure there's thousands and thousands of possible profiles, right? You can have a single layer, you can have many layers, you can have your bedrock pretty high up, or you can have it very far down. Maybe you have a lot of soil layers and your borehole never reaches bedrock, like this boy here. It never reached it. It never reached it. We're at less than 500. We just stopped drilling. Money ran out. So all of these are not the same just because they have the same VS30. And of course, even if we say it's rock, we can imagine a lot of different kinds of profiles that would be considered as rock for Eurocode 8. So I want you to be aware of the vast variety there is in nature and natural geological formations compared to this one number that of necessity we need to come up with and just put in a table in order to categorize. Everything that falls into B is not going to behave the same, and we're going to see that as we move on with our class. So I'm kind of foreshadowing a little bit, and I'll be moving in circles a little bit in order to foreshadow, get you to think and consider, and then we'll be seeing answers and explaining rationales, etc. as we move forward. Now, to look at a different thing in this table, we're going to take our time with it, because if there's one thing I want you to leave knowing, or not knowing, is this. So in the stratigraphic profile description, you see words like dense sand, gravel, very stiff clay, etc. So sand, gravel, clay, dense, loose. I don't know if these ring any bells, but I have a couple of slides to either refresh your memories or just give you a little information if you haven't been taught that. So anything that has grains, so clay, and is obviously dry. So to do these tests, we put the soil in the oven first for a while, overnight. It can be clay, silt, sand, gravel, obviously not a big fat rock, anything that you can kind of pick up and let run through your fingers, you can do this test with. So there's different sieves with different, I'll show you here, with different little slits through them. So a sieve is what you use, for example, to drain pasta, right? Just imagine your pasta is really, really minuscule and it's your soil. So you let it go through the sieve and the fat collected immediately, the less, the thinner, finer, make it to the final one until you have some kind of powder. So if you put all of those in a graph with the diameter of the grains that pass, you get a little plot like this. So this is your grain size distribution. So you can categorize whether you have sand, if most of it falls in here, like in this case. If it were very thick, you would be a little silly if you took gravel and this, but it would all stop in the first fat pasta strain. And then if it's like very, very powdery, like silt and clay, it's gonna fall into the last one, so you would see it mostly here. So this is an example of finer to the right, coarser to the left, and unsorted. And I want you to take just 10 seconds to think about, what does this slope mean? How steep is the slope? What does it mean with respect to how homogeneous it is? And that can also feed into density later. So nobody's answering, but the two ones which know what they are, so the two ones that know what they are steeper. And the one that doesn't, which is unsorted, so kind of here, kind of there, is more shallow, right? The dark one. And actually, this is a really cool plot, I think, because these specimens were done on a simulant soil from Mars. So it was made somewhere in Texas or wherever, but it simulates the Martian regolith at different grain size distributions that we did some tests on a couple of years back in the UK. So now you know a bit more about what this guy means by clay, sand, gravel, etc. Gravels, you can see them. They're like this. Sand, gravel has a bit of both. Clay, silt, it can't even run through your fingers. And if it's wet, you can just hold it and it's one big lump. This brings us actually to another term we find here, which is cohesion. In the softer ones, obviously, in the rock category, you're not going to be talking about clay and very fine materials, but you'll see that in the softer ones, we start talking about cohesion. Cohesionless soil, that's sand. Cohesive soil, that's clay. And to give you an idea, and if you see this, you'll immediately know whether you've done soil mechanics or not. Cohesionless is going to look like this. It's going to run through your fingers. If you build a castle made of sand, if it's wet, it's okay. After a while, it crumbles. If you have something very, very fine, like silty clay, it can do this. This is dry, but you see, it's standing. I took it out of the mold and it's standing. Sometimes you drive and you see these red slopes and they can be dry but pretty steep. That's clay. Clay has cohesion. It's a mechanism of shear strength, because anything that doesn't have shear strength cannot stand like this. It can be poured into something and I can punch it, so it's okay with compression. Dun, 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 I can sit on it, it's fine, it's compressive. But if I try and shear it, it's not going to do good. So to sit like this, it needs to have some kind of shear strength. And clay has the type of shear strength that we call cohesion. It's kind of like the grains kind of stick into each other. So this is something the sand wouldn't have. That's why it needs the water on the beach. So cohesion is one of the mechanisms of shear strength. And the reason I care about shear strength, and I'm taking you into this little soil mechanics side tour, is because that's what hurts when we have an earthquake. The material is sheared. Shearing is, for example, this is shearing. I reached the shear strength of paper and I surpassed it. Now I haven't. I'm giving it more and more, and now I have. So similarly, I don't have soil to show you, but similarly, when soil undergoes seismic action, it's sheared. So it has two mechanisms to withstand that. And one is cohesion, so clays and very fine materials are good with that. And the other is the angle of friction. If you have anything like wallet and you put it on any surface, like my hand, this is an interface. Any interface in the word has its own angle of friction that characterizes it. And if it's not two different things, but it's the same thing, soil over soil, it's sheared by an earthquake, this soil-soil interface has an internal angle of friction. What does that mean? Let's put this. If I exert a lot of vertical, so normal stress to the interface, then I can't really push it. If I don't, and it's not a very strong vertical force, just the little weight of the iPhone, then I can push it. If I push it and it moves like it did now, I overcame the angle of friction. So basically, if I overcome these things for a soil, it's yielded. You might have seen this as the Mohr circle. If it increases in stress, at some point it's going to touch the Mohr Coulomb envelope. This is your shear stress envelope, and it breaks. So you've seen similar things for concrete, I'm sure. And basically, this is kind of wrapping up what clays are good at and what sands are good at. Sands are mostly good at friction, and clays are good at this. Cheap, or rather free strength, because you don't need to be pushing downward on the interface. See? You find it at normal stress 0, whereas for friction to work, you need to be exerting this normal perpendicular to the interface stress, which is why this is going upwards, because we're gaining a little bit with friction as we push harder onto our interface. So now you know a hell of a lot more about what's behind all these terms. And let's go to the second column. This is, it says NSPT, Standard Penetration Test Number. And if any of you know about it, you can feel free to say so in the chat. But I'm going to show you anyway, just as a very brief intro. So to do SPT, first of all, and big difference with VS, you definitely need a borehole. VS, you can have it from surface geophysics, so non-intrusive. You don't have to dig at all. Just put your geophones or seismometer on top, measure the noise, and then do some magic, and ta-da, you get a shear wave velocity profile. You need to pay, but you don't need to drill. For SPT, you need to drill, and you only have it at those locations where you stop drilling and you start doing the test. You basically have a hammer and you knock a lot of times. And you count how many times you need to knock for it to go in by, let's say, 30 centimeters, etc. So it's a really terrible test in terms of accuracy, like really, really terrible. But folks have been doing it for decades. So there's huge databases accumulated and empirical knowledge based on that, which is the only thing it's got running for it. So if you know an SPT from geotechnic folks who've done that, it's good. You can go to your table and use it to use kind of an average value for your profile to characterize your soil. Of course, you need to look also at the cores and the descriptions that the engineers give you, etc., etc. So this, I'm not going to go through it. It's all the different ways that it can go wrong and the corrections we need to do for it. So I'll just leave it for you there, just for your general education. And this is what an SPT profile could look like. Again, shamelessly stolen from the internet. These are from Japan. You would have known it even if I didn't tell you. So you have some descriptions, also in English. Here you see rock. So you can imagine that we won't have a value for rock. We're not going to be hammering a little hammer if we hit rock. It's pretty useless, right? It's not going to register any number. It's not going to move in by 30 centimeters. It's just going to say, nope, I'm staying right here. So this is kind of the note, I'm staying right here. We usually take it at a value of 50. And what do you see? For the first 5 meters depth, I don't need to hammer too much, and it's going in, right? So these are very small, sorry, what are we? These are very small numbers, like less than 10 for 5 meters. What do you know by looking at that? I have something very soft for 5 meters, and then something very hard. So this is kind of similar here too. 4 meters, and then it increases very fast. So what kind of a soil would that be? You basically have rock at 5, 6, 7 meters. How would you classify it? If we go back. Formation ground type A, rock, says including at most 5 meters of weaker material. We're flirting with that, aren't we? Otherwise, we get deposits, but it says at least several tens of meters. This is kind of a different game, right? So we might be tempted to say, this is probably a rock with some surface topsoil. This is an example where they had the 3 different boreholes nearby. So can you see at some point on how they all differ? So there's a lot of scatter, even from point to point, just like Terzaghi promised. It's made by nature, not by man. So it's going to be very heterogeneous. And if I drill this and not that, then I'll never have an idea of this huge variability, right? Look at this depth at 15 meters. This borehole says this, that borehole says that. Very, very different. Also, you can see we sometimes have reversals, so hard material and then underlain by soil, not a nice situation to be in. So this we've seen. You can also try later to kind of gauge where we're at. And I'm going to show you one last example. This is from Greece, where I did my PhD in Aegeon, which is in the Corinth Gulf. We already know, because of a hell of a lot of measurements, what we have. But let's see if you can identify it. So here we have a lot of soil layers overlying a stiff conglomerate, which is quasi-rock, and then very deep rock that we're not going to drill down. This is 100 meters here, okay? So if I were to show you these, this is SPT, point to point. Here it was this, here it was that, so it jiggles a little bit, but at some point onwards, it's asymptotic at 50. This value here is 50. And this is your VS, and this is what it does, your VS and your stiffness, which is basically your VS squared. Can you imagine what's going on here? Does this tell you anything about where your interface with the rock is? Because where it is going to help us classify the site. "10, 20, and 30 meters. Please pick a number. Where do you think you have the interface? 10, 20, 30. Just very roughly. Achilles is putting you out of your misery. So, indeed, here we reach the asymptotic value. It started saying, no, 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 I won't budge. And the VS and the stiffness is saying, whoa, dude, something's happening. So we've reached the interface between the deposits and the conglomerate, right? So we've gone through VS30, SPT, cohesion, sand, clay, soil types, classifications, and all that. And by the way, this last little column, which is undrained shear strength, this is for clays, and it's related to the cohesion I told you about, but it's a little too much of a deviation to go there. So this is going to tie into the Eurocode's design spectra, and I'm wondering if you need a break already, or if we should go through these. I meant to have a break after these, but you guys can tell me how you're feeling. It's now we've had an hour. Should I give you 10 minutes and we'll reconvene at 5 past? And it'll give me a chance to struggle with the microphone issue. So yeah, I'll make the decision for you this time, and I'll break for 10, 12 minutes or what have you, and try and sort myself out here, okay? In the meantime, I'll stop sharing and I'll ask Demetrius if we might try. Okay, hello again, everybody. Good, so we're back, and I found out the reason for our trouble, so now I can hear you. And I hope it will make a difference. So please don't be shy, and please do interrupt if you would like to ask something. It would be so much nicer if we were in a real classroom. So talking to you rather than myself would help give me that illusion. So here we are again. And we've had a good look at almost all of the parameters written in this table of Eurocode 8. I suppose you do, of course, have all the PDF files of the Eurocode. It's hundreds of pages, the different parts, but you can easily find what you want just with a find, just write the word VS or ground or soil or something like that. So we won't go into anything about the special cases, but through what we're gonna go over these 2 days, I think you'll understand that special cases really merit a site-specific investigation, and that I think basically no legislator could just give a spectrum or a value without having additional information. So we're gonna push on and make the connection with the Eurocode spectra. So I'm sure you've seen this. What I don't know is exactly in what context, and if you have paid a lot of attention to the different types of spectra in terms of seismicity, and the different types of spectra in terms of site classes. I'll try and visualize the chat. Oops, okay, just in case somebody writes something, I'll try and keep an eye out, but I'll be assuming that you'll just give me a shout if you need to. So this is your design spectrum with oscillator period, and you know, it's anchored a particular point, and that's going to be one of our foci, plural of focus, today from now on. And you have your plateau and your control frequencies, and this is so in my life, at least, I've only ever looked at these things at a 5% damping ratio, so for reinforced concrete. And the first thing I want to say is, because we're going to be looking at damping in a bit, damping for soil, I am very happy for you to keep in mind the damping of concrete as we do that, but I want you to be very clear that we'll be talking about two different materials. So as any material on the face of this earth has damping, meaning any oscillation within it is not going to go on forever. Otherwise, I guess we would have ways to have free energy. We have a damping ratio. So quick foreshadowing to the damping ratio of soils, which we're going to look at in maybe half an hour or more. So of course, there's also spectra given for the vertical component. We're going to focus here on the horizontal component of ground motion. And we're going to have a look at how this little guy, S, and the control periods depend on soil, and how, and you know, of course, that it's normalized by this little guy, SG, which you also know about, but we're going to make the connection just to be, you know, to go a nice full circle today. So, excuse me. You've probably noticed that there's two types of spectra in the Eurocode 8, and actually I'll just jump forward because it never ceases to amaze me how badly this has been phrased. I mean, if I had to make people understand the two types of spectra, I would not do this. So this is a note underneath a plot, and you need to deep dig into it to see, for the purpose of PSHA, PSHA, if we expect a magnitude not greater than 5.5, weirdest way ever to phrase it, it's recommended to adopt type 2. The only worst thing could have been not to adopt type 1. So negative here, positive there. The bottom line is, and I've made the plot to make it a bit easier on you, magnitude bigger than 5.5, type 1. Magnitude less than 5.5, type 2. And that's all they needed to say. I don't know why it was so hard. And I want you to focus right now, let's say, on A, so the lowest one, okay? Let's say for rock. Let's not focus on the soils. Rock here, rock there. Do you notice a difference? What are we doing? We are basically taking the right-hand part of the plateau and we're pulling it to the right. So why are we pulling the spectrums here when we have a larger magnitude? I don't expect you to know it. I would be happy if you did. I'm going to tell you if you don't. Why are we pulling its ear to make it go towards longer periods? It's what we're doing. This is the major difference between the top and the bottom plot, right? And we're making the distinction based on magnitude.
Maybe we expect the excitation period of the earthquake to be at a larger second.
Bravo, Maria. Excellent. Yes. So a large earthquake is, first of all, in terms of the earthquake source, very rich in low frequencies. So long periods is where it's probably going to harm us more. And the second reason is that a very large earthquake is going to impact areas at longer distances too. And when you get to longer distances, thinking of short and long periods or high and low frequencies, it is again the long periods or short, small frequencies which will survive with the attenuation. So for both those reasons, we're pulling its ear to force it to cover a little more of the ground here. So here we were kind of not covered, and now we are at longer periods. And of course, as you can imagine, when it says go look at your likely sources, you need to know where your faults are. I didn't have time to give you a plot of the tectonics, the faults in Greece or the seismicity. Well, you can do that just entering our website at the National Observatory if you want to look at seismicity. But basically, both of those things have fed, and politics, a lot of politics, have fed into this map. So you know the Aegean or the Hellenic arc here, and that you have very strong seismicity. So this can explain the red in the Ionians. Of course, what happens in Athens or Thessalonica, when you see these kinds of lines, this is more explained likely by politics and administration. But be it as it may, you can also revert to here and have a look and correlate with the maximum expected accelerations, because you can choose your source based on actual scientific knowledge of where your sources lie and where the big earthquakes have happened in historical years, and how far is fault X or Y from where you are. All of that can feed into whether you believe your site of study is affected by this type of earthquake or that, and then based on this you make your choice. But now we need this little AG in order to help us anchor our spectrum. And the AG, whether it's based on science and or admin politics, is going to be taken from here, because the Eurocode tells us to go look at our national annexes. So this is it right now. So maximum expected peak ground acceleration, PGA. Does everybody know what PGA is? If I show you an accelerogram, you just grab its largest value in the time domain, and that's it. That's your PGA. And we'll also see where it lies on the response spectrum later on. So maximum, if you're in these islands, 036G, and this is assumed on rock, means it's pretty damn high, because as we're going to see, on soil this can amplify a lot. Intermediate zone 024G and the least seismic zone 016G. If you ever bump into an old version of this map that also gives you 012G, it's got 4 regions, don't take it into account, because that's been superseded by this one here. So this is where we take our AG value. If I told you that the site is located, I don't know, Aegean, for example, which I showed you. I know what it is because I studied it. It's kind of here or there, embarrassing, not sure which, but it's well into the zone 2, 024G. Grab it, then we can unnormalize our spectrum. So multiply with this and move on. Final piece of information. We're anchoring everything at S, and Eurocode gives us S as well as the control period values as a function for each type of spectrum, type 1 and type 2, so this is just one of them, as a function of the soil classification, which was this little table that we went through in painful detail in the last hour. And what does it say? It's not really very straightforward. So you have A, B, C, D, E, so from good to worse. What would you expect? You would expect that A is the reference site, so it gets 1. Obviously, it would be silly to have anything other than 1, because this is just a factor to normalize things. And for softer sites, it increases 20%, 15%, 35%, 40%. I can tell you right now, this can be bigger in the real world. But of course, we design not only for, well, we also design for what we can afford and for what, my grandma in the village can afford to build. So it's not going to capture everything. What else do you notice? The control periods, B, C, D. Okay, D is the same. It doesn't change. Look at D, TB and TC. As you move down from A to softer sites, these control periods increase. We can see this also here. See, we were talking about type 1 versus type 2, but within the same type, going from A to B to C to D to E, see how again we're pulling the ear up and to the right. Up and to the right, we expect amplification, so we go up, like we went up in the S. We also go up, obviously, in the 2.5S, whatever, and we move to the right. We are capturing more and more of the long periods, smaller frequencies. So this is again telling you what? That the soil sites are gonna be active, just like the big earthquake sources, in longer periods. So because we need our buildings with such oscillator periods to be protected, we pull the ear. So here we are. And these are the tables for the two types, type 1 and 2, bigger and smaller than magnitude 5.5. And here you have it, your plots, your design spectra with your corresponding numbers. So we said why we're pulling the spectrums here again. We did it once between type 1 and 2. For the magnitude means the characteristics of the earthquake source. And we're doing it again within the same category each time. Also here, though you can't see it, but it's moving slightly to the right. But here you can see it clearer because of the scale. So we're pulling it one last time to account for the type of the soil. And as we said, the only thing we have to inform us here about the type of soil site we have is this letter, A, B, C, D, E. But as you can imagine, within the A, you can have a VS30 of 800, you can have a VS30 of, well, if you're in Canada, of 2000 or 3000. Or if you're in Finland, they have some ridiculously hard rock that actually outcrops, which could be actually 3,000 meters per second, and you can just walk over it. So is that the same as the puny quasi rock we saw before, where we had this Hokkaido site with 5 meters of disgustingly soft soil, and then the jump of the SPT to rock, so more than 800 probably? Well, the quick answer is no, they're not going to behave the same. And this is one of the drawbacks or one of the limitations of any code, not just the Eurocode, any code, that I would like you to be aware. So we're doing the best we can right now. It's nearly not where it should be. So science is pushing forward with this kind of knowledge, how different sites and soils affect ground motion, etc. And the codes are going to pick up on that and very slowly, like an old lazy man, try and put on their pajamas or put on a new set of pajamas because we found some new research that says this or that. And then, 10, 15 years later, we have something better. But that's the way things go. Because when it's in the codes, then people need to pay for it. So we need to be a little careful, I suppose, what we make them pay for. So this is just a glimpse of not the Eurocode, but how it compares to the American code, NEHRP. And the main thing is that we kind of have the same category limits, 180 and 360. Instead of 800, we have 760, which is, let's face it, practically the same thing. But they give them different letters. Where we had E, they have D. Where we had A, they have B. So for them, soft rock, is 760 to 1500. And because they also have a lot of outcropping hard rock in the central east, so let's say towards, towards New York, to make it easy, they have harder rock. They also have a special category, and that's what they call A. So that would be our A star, if you will. So just be aware that they're similar, but there's one category shift. They're not the same. So just a few seconds of a micro break, because this is where I was gonna end before the proper break. So think of cats or whatever it is that makes you tick. And take a couple of breaths, and we move into the next, let's say, little section. And I'll start with, so we're going to start looking at ground motion and site amplification. All of this was what we have in codes, what we have in practice to characterize sites. And once we've done it, what the codes tell us to do with a design action, with a base shear or what have you. So we're going to start looking more into the heart of the matter, which is side effects. And I'll start by just clarifying a little something, just to be absolutely sure it's straight in everybody's heads. So can somebody tell me the difference between magnitude and what we call ground motion intensity measures? And I'm sure you've already done this in the first semester. So what are ground motion intensity measures and what's magnitude? Are they the same? Are they not?
I think that the magnitude has to do with the energy released from the earthquake, and the intensity measure has to do with how, for example, the structure or the soil is affected from this motion.
At different?
I'm sorry?
At different?
At different periods, for example, the intensity measures.
Okay. And the location. So excellent. Thank you. So apparently you have voted for Maria as your spokesperson and you have chosen wisely. Next time I would also like to hear from others, of course. So at the source is the magnitude. It's an absolute measure. One earthquake has, well, maybe it has 2 or 3 magnitudes, local, surface wave, moment, etc. But basically, we all of us agree on the magnitude. But you feel it at very many different sites and locations. And these locations might, of course, have very different geological soil conditions. And of course, we can quantify the feel of it, so the intensity measure, at different frequencies or periods, like you said. So we can have peak values or values at a particular oscillator period if we're talking about PSA, etc. Right? Of course, we also have macroseismic intensity. We don't really matter. The important thing is that they depend not only on magnitude, but also on distance, and also, which is the heart of this course, site conditions. And so they are relative. They're not absolute. And as my old-time hero, Norm Abrahamson, says, engineers don't design for earthquakes per se, but for ground motions. So this is why we need to understand the ground motions we have at a particular site. And actually, right now, even in international research, the number one factor of uncertainty is the site response. So this brings us into basically site effects. And I have a few prelim things, which again, you will probably have heard, but we're gonna just use them as little Lego blocks to build into the main part. So all of you know, I think, that if I have an accelerograph here, and I'm living in this building, for example, which is inside this basin, as it seems, and there's an earthquake here at this distance, x, what I record here and what I feel, so the ground motion, will depend on a bunch of things. It will depend on source parameters and features, on the path features, and our favorite, closest to our heart, the site geology and the site parameters, right? And usually you would do your PSHA and look at all the different possible source regions and how far they are, etc., etc. And you would assume at some point that you are on rock, right? And then you might want to do a site-specific study to bring that to the surface, at least for example, for critical infrastructure and high importance buildings and infrastructures like, I don't know, nukes, which is what I've worked on, and a lot of other things of importance. You might do your PSHA and get what you have, let's say, here at the base, and then you would have your site response specialists bring that motion up to the surface. Because you recognize the huge variability and hence uncertainty that you bring in. So this is what we're trying to build in here. You've established all of your wonderful background in PSHA, and now we're just going to build a little bit on top of it, as it were, for the final layers of the Earth. So here at the source, you have the magnitude, excellently captured by how much energy is released. Of course, you also have your rupture mechanisms. You might have heard of strike slip, normal, reverse faulting, etc. It's not the time for this, but I want you to know it fits into this box. You also have the path. Of course, all of you know that if somebody announces an earthquake, you're gonna ask, okay, how far is it from me, right? And then a seismologist would ask, what's the magnitude? Period. That's all they care about. We. An engineer will ask, what's the PGA? What's the PGA? So what was the largest shaking there was? And, you know, if you live somewhere in the vicinity, you will ask, how far was it? And you'll kind of gauge if it's of import to you or danger to you or not, right? Why is that? Because with distance, with a path, there's two mechanisms chewing away at your energy at all frequencies. Geometric spreading, which is basically partitioning the energy. If you imagine a spherical wavefront, which is a sphere, and I happen to have one, which starts like this, like a little tennis ball, gets bigger, 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 then the energy you have here, as this will get bigger and bigger, is going to be distributed to a larger surface. So it's going to be attenuating at the particular point as the sphere gets bigger. And you also have material absorption. So the material is not perfect. It has little cracks and things, and it's gonna eat up your energy. So that's your quality factor, if you've heard about that. So those two mechanisms feed into the path. And for example, the attenuation is what will primarily decide what your duration is. And do you care to tell me very roughly what the duration of a typical seismogram you have seen might be? Or if you've done any structural analysis, what was your input motion? How many seconds of a little time history did you input? Or if you've felt an earthquake, or if you've seen a recording. Order of magnitude. A few milliseconds, a few seconds, a few hours? I can't make a Kahoot quiz for everything, so just tell me. Did anybody ever feel an earthquake? How long were you shaking for?
A few seconds.
Okay, exactly. And who was the one who felt it? I can only see Maria here, but anyway, it wasn't her. So these are, just to make things a little more interesting and funny, these are a few moonquake recordings from the Apollo mission in the 70s. They installed seismographs, very, very old-fashioned ones. And these are seconds on the y-axis. So this one was going on for about 30 minutes. And it turns out that the attenuation, these factors on the moon, are very different, and it's much less attenuating. So imagine that. But this is to say that duration is also defined, well, of course, by the source, A big earthquake is going to break many kilometers worth of fault. It's going to rupture them. That's going to take a while. Then if it's far away, that's also going to take a while. And then the duration is going to decrease if this path eats up the energy more and more, if it's more attenuative. And then we come to the site, our favorite. And this is also going to affect many things, including which duration. So now we're starting to go to our main focus, which is the local soil conditions. And I've used this cartoon here because I think it encapsulates a lot of the things that could be happening. You might be on a hill, you might be on a trough at the foot of a hill, you might be inside a basin, you might be at the edge of a basin. And look at all that's going on beneath your feet, which you might never know. Different layers. We don't know how many there are, what their properties are, if they're inclined at some point, like the edge of a basin, if you might have had a fault going like this, and then you might have lateral variabilities. There's a whole bunch of stuff going on. And this is just the geometry, right? This is what you can draw. And then we come to the material properties, much like concrete, as we said, you know it's damping, it's 5%. You probably know its compressive strength in megapascal, and you might know its Poisson or this or that. Its weight, I can't recall, but maybe it's, I don't know, more than 25, I don't know, 2.5 or more tons per cubic meter. So you have material properties. These in geomaterials might be what? Wave velocity, density, of course, everything has some weight, damping. And the main uppermost thing that will capture our attention is wave velocity. And which of all the waves we saw in the first little figure? P, S, Rayleigh, Love. Which is the key wave velocity we care about? The one that gives us the strongest shaking in the horizontal direction? S waves. Dimitra was a bit shy, but she answered in the chat. Thank you, Dimitra. So S wave velocity, right? Vs. Whenever we mention velocity, unless otherwise stated, it's Vs. So look at this little basin here. If anybody is from Thessaloniki, the best place to be and eat. This is not far from Thessaloniki. It's the Euro size test. It's a bunch of accelerometers in an array covering a basin, and this is what it looks like, which is why it's very interesting, and they studied it. So we know what it's like, and we have accelerometers all around here. We know the soil properties and the geometry. Look at what effect they have on what we record. This is the same earthquake happening, so same source, same energy released, same duration of the source, same path. If this is 1 kilometer that I'm showing you, this may have come from like 50 kilometers or 100. So this dimension is negligible compared to the source distance, right? So all of these are basically a point, the way the earthquake sees them, but they are so different. Why? Because of the local soil conditions. This guy here, lucky guy, he has his house on a, let's say, on a hill. Here too. These guys close to the basin edge, basin center. Which features of the ground motion can you see change? The amplitude for sure, blue versus red, and this is what we call the PGA, right? We just grab the largest, in absolute terms, number we see in the time series, and if it's acceleration, and that's PGA. Also, can you see the duration changing? We've cut the recording here, but you can imagine it goes on, right? So until it comes to become noise, it's going to be a much larger duration than what you have outside the basin. And the frequency content. I don't know if you can see, but can you notice? Let's try and spoil it. Maybe you can see now. Can you see here? This it's pretty sparse. It's like I had an accordion and I pulled it open, right? Whereas the P waves, of course, and here on the rock, it's like I pushed it in again. So if I open the accordion, obviously, longer wavelengths, lower frequencies, longer periods, right? So all of these are effects on ground motion, and we can see them in the time domain as we just did. And of course, we can see them in the frequency domain. So in the spectra, these are Fourier spectra here on rock and soil. And you can see exactly this pulling of the ear, can't you? You can see how the rock is richer in low periods, meaning high frequencies, and how the soil is richer in longer periods, just like we pulled the ear of our design spectrum in order to cover longer periods. That was the idea when we're dealing with softer sides, when we're going from the A side to B, C, D. This is what we're doing. This might be an A side, and this is definitely a C or worse. So we've pulled the spectrum's ear, and then you can see in the Fourier spectrum of the recordings that we did well. And in the response spectra, which are, of course, less fuzzy and more nice and shapely and smooth, you can see that you often have this bump at longer periods from deeper, softer soil deposits compared to this early on high frequency bump, which you see on the rock. So we've seen these effects of the soil in all possible domains. Time domain, proper frequency, so seismological Fourier frequency, and oscillator frequency or period, which means response spectral domain, right? We're going to look at the differences between the two spectra, a bit of theory next time. And of course, obviously, you can see it in acceleration, velocity, and displacements. And you know better than me, because you're proper engineers, which one of these is proportional to earthquake forces when you're thinking of your base shear. And one of them is with the help of mass and Newton's law. So you very much care about whether all of these features of his or hers have been changed by going from the assumption of rock to go into a soil site. Because there's villages here and people might have structures here, right? So this is my mental break. Take a few seconds thinking of cats or something else that's really nice. And I'll find my other presentation. And to help you, here's a cat. This is him. This is Mr. Pickles. This is the only good thing about Zoom and homeschooling. So, side effects. How do we observe them? And I think I would like to give you another 10 minutes to take a breather and go into this last part. So is 10 minutes good for you? I'll be back at 5, yeah, 5:02. Yeah, 10:55. I'll stop sharing until then. Okay, back for the final part, and we'll finally get to do a few simplified calcs. All right. So I'll show you a few typical cases of observed effects of the surface geology. So we saw a few harmless little time series, but you can see those even when there's, you know, not much going on. We'll also see a few bits and pieces of damage, just as a broad overview of side effects, and then we'll come back to what we can do by hand, which is where we should start, which is the 1D. So what we said before. So it's possible that the first side effect observed was more than 100 years ago in southern France. there is, or at least thought of it that way, I'm sure there were things before, there's this little hill, and all around, well, on and around this hill there was damage, whereas further from it and at the toe, there was not so much. So it was the first time, I think, that they observed this kind of concentration of damage. So the first years were also, of course, only macroseismic. But the real site effect era started, as you know from your first class, I think, with the big Mexico earthquake, which is now more than 30 years ago. And so this picture is from there, and there's a lot worse. So there was a particular class of tall buildings which were affected, and I'm going to apologize for my French. This is buildings of 10 to 30 stories were mostly damaged, is what it says here. Of course, you can also Google Translate. And one of the first observations, this was one of the first huge observations of 1D amplification and its potential to destroy, and we'll see this in the numbers in a bit. There's also more complex things, as we saw the topography is a more complex phenomenon. You can't solve it with a pen so easily. In Kobe, there was the first macroseismic damage observation of amplification of ground motion. They called it the damage belt. It was the edge of, let's say, a basin. So at one side, there was a concentration of damage. You can see this line here. And on the other, there was not. So this is, of course, a 2D elongated effect. Also in Mexico, in the recent earthquake, these are different zones around the city, and there was concentration in terms of 2D effects going from the very soft city center sediments towards the hill zone. So there was concentration at the edge, at the transition zone, which is very much a 2D effect. Of course, sometimes you have more complex things like 3D. This is not even a straight basin. Any way you choose to cut a cross section, it's going to look different. This is in Grenoble, France. And you can see even the base of the basin is really, really far from being easy to model. So here you would have much more complex effects. This is again some time series from an array, the same earthquake and how it's recorded at different places on the rock and at different parts of the surface. You see the difference in the amplitude and the frequency content and the duration. Garner Valley is a famous example from the 90s. Lots of work done there, lots of money spent. Soils over rock, looking at how site effects work. And of course, a special case of site effects is nonlinearity and liquefaction. And if anybody ever tells you about liquefaction, I'm going to bet you €5 now they're going to show you this famous picture of a building complex in Japan, some of which buildings completely toppled, whereas structurally they were fine. So this is really a clear indication of local soil failure. So geotechnical failure all the way when you see a whole building just falling on its side. It's from the ground and below that it happened. And from all of these varied and complex, some of them complex types of site effects, we're going to now focus on the simple soil over bedrock case. So the simplest thing we can imagine, to try and get our pencils and calculators and papers ready and see what we can calculate, which is better than what the Eurocode can do, but of course less than what a computer could do with more data. So keeping in mind, quick reminder of frequency, period, velocity, and wavelength, because we'll be moving in their word from now on. So you all know that frequency is the inverse of period, okay? And when we are talking about waves traveling within a specific medium, let's say a specific soil, which has a specific Vs, a velocity, then what is a wavelength? It is the length it travels within one period, right? If we imagine, because it's the easiest thing, a sinusoidal wave, you know, one period is this. If we plot it with time, it does this, it's come full circle. If it continues, that's a second period. This is a third period, etc. So how much space did it cover? So how much distance did it cover in space in that one period? That's the wavelength. So it's a period times the Vs, or Vs divided by frequency. And wavelengths are kind of the way that waves, let's say, perceive the medium they're going through. And depending on their wavelength, they perceive or not the obstacles they find. So, okay, this is what I said, either with, when I plot it with time, this is one period. When I plot it with distance, this is one wavelength. And if I tweak the frequency, or if I tweak the velocity, which is to say the same thing, as you see, I can fit, let's say, two periods, two wavelengths into the initial one. If I were to double the frequency or double the velocity in which the wave travels. So I want you to imagine, let's say you're a wave and you travel through a very, very fast medium. So you have a very high frequency. You're traveling like this, very fast, up and down, up and down, up and down, up and down. Whereas if your friend were a wave traveling through a very much softer material, like a soil, they would appear much lazier than you. Their wavelength would look like this, much lower velocity. So covering bigger distance at short periods of time. Of course, that kind of wave is more enduring. So the first one, like the little child jumping around with a lot of energy, that can cover like a lot of cycles in a short time, that gets tired easily. So tired in our terms in waves, that's attenuation or damping, if you will. So one gets attenuated faster, one doesn't. And depending on these glasses you're wearing and these kinds of lengths you're used to covering, you may or you may not see things. So if this were in front of me, oops, okay, I'll do this, and I were the high frequency wave going like this, I would not really even perceive this kind of length. It's many times bigger than my wavelength. Whereas if I am one of those lazy, slow waves with this kind of long wavelength, and you put in front of me the point, I don't know, the point of this little pencil, I'll just go through it and I won't even see it. So we care about wavelength because the waves will perceive and they will be amplified, de-amplified, etc. when they come to features which have a similar dimension to that wavelength. That's why I say it's, you know, they're wearing those kinds of glasses. So let's see how 1D amplification works. So this is the simplest possible example that we could think of. Let's imagine we have a wonderful bedrock and a layer of soil on top, and we have an upcoming wave. Let's say it's a very simple S wave, okay? So maybe a sinusoidal thingy, whatever, right? Coming up. Normally, if there were no soil layer here, it would hit the surface and come back down, right? That would be it. Here, there's an interface. Why do I say there's an interface? Because there is a difference between these two materials, the soil I have here, and the assumed rock half space. Half space means I'm not expecting anything to change. It just goes down forever and ever. It's just it's a big assumption. It's just a simplification. So what is the key difference? I want you to answer that between these two things. And I'll visualize the chat in order to be able to see anything you write. So you can even see it here, but you can see many differences. Somebody tell me what is the key thing I care about? In what do they differ? What's gonna trigger everything? Soil and rock, according to the Eurocode table. How do you classify things? What was the first column we explained? And the calculation you did by hand? I'll start calling if you don't volunteer. Hamdi, are you there? Okay. We have VS30. Okay, VS30 is what we computed. But VS30, there is one VS30 for this profile. And actually, if this is 30 meters as it says, the VS30 is equal to the VS of this material. Now, go from VS30, which is something that defines the whole profile, to the property that defines each individual material that makes up this profile, which is VS. We did VS1, H1, VS2, H2. I shared it, but it's here, right? We had VS2, 300, 500, and 1000. Each of these layers had its own property, the velocity at which the wave travels within it. When it's here, it travels at 2500 meters per second. When it goes into this, suddenly it's really, really soft and slow, and it travels at 350. Of course, this is an idealized case. You'll never see such an abrupt change. But okay, this is the key change. The difference between these two is the key reason that you have upcoming waves, and then some of them go through and they're transmitted, and some of them are reflected and go back down. Those we don't care about anymore because they're just going to go down, they're not going to find any other interface, and they're going to die eventually. But the ones that are transmitted, what's going to happen to them? They're going to reach the surface and then? Iro? Oh, Ira, was it?
Yes, and then they are going to give us. I'm sorry. Θα διεγείρουν και την επιφάνεια.
Okay.
I'm sorry for the Greek.
Okay. Okay, they reach the surface. Oh God, what's the word? Okay, they will. Your answer is they'll excite the surface, sure. But after this, where are they going to turn to? Where are they going to go? Can the waves go into the air? No. So they're gonna do what?
Energy will be made into something else. So
Okay,
they
we're gonna lose some of the energy from friction. I agree with you. But what survives is going to come back down, right? If I didn't even have a layer, I said it would go up and then come back down. So with this layer, again, the survivors, those who didn't go back down, will go up to the surface and then back down. And the second time, part of it is going to go away again. It's going to be transmitted into the faster layer, and part of it is going to get reflected again. And the reflected one is going to get re-reflected at the surface. And as I show it, it looks like it goes on forever. It doesn't. So if I were honest, each time the amplitude is going to decrease, right? But you have to imagine this is not in space. It's all on top of each other. So this is basically the phenomenon of the resonance, of the trapping of the waves. As Ira said, we're going to lose energy. It's going to be transmitted into something else. So in high school, he said, you know, in a machine, we would lose energy. It would be transmitted into thermic energy, for example. Here, basically, it's attenuation that's eating away. But what is not eaten is basically reverberating, right? It's this little layer, and the waves are going up and down, parts of them, smaller and smaller parts, but these are falling on top of the new incoming ones. So this is creating a big resonance. And this is what we're going to study from now on. And this resonance, as I said before, it's going to depend on the geometrical features. So how do I draw this in paper? What are the key characteristics of the geometry of the soil profile? And what are the key material properties? And you see all of it here already. You see a depth of the layer, a thickness of the layer. This is the first key bit. It's the geometry. Of course, we assume it's 1D, so it's horizontal. And we did ourselves a favor and we said there's no intermediate layers. It's just one layer and then rock. This is the simplest we can make it. But we have this thickness. And we have these material properties, Vs for the first, Vs for the second, and different densities. Of course, rock is going to weigh a little more, right? So different specific densities. And if we came to it, they would also have different damping values. So there you have them, geometry in red, material properties in blue. And I'm telling you that where the interface is will determine the first key thing. It will determine at which frequency will these waves resonate. So what is the resonant frequency of this entire soil column? It's the easiest formula to remember ever. So the way I remember it is with period. I usually say period is 4h to Vs. If you want frequency, it's Vs to 4 thickness. The way you can think of it is, okay, which Vs, first of all? I know the Vs of this layer and of that. Which is the only one I care about in this case? Where are the trapped waves?
On the soil layer.
Brava, exactly. So I care about Vs in the top layer. At this point, if I deleted everything in here and I just said rock, you wouldn't care. Vs and thickness of layer. So this first thing is defined only by how far down is the thickness of the layer and how fast is it. 4 times Vs, you can just think about the wave being trapped and going up, down. Once, twice, that's 4 times the h. If you want, you can think of it like this. And 1, 2, 3, 4, it's trapped. Vs to 4h. Okay, let's get the fundamental period and frequency of this layer now. You have 30 seconds. You don't need more. Okay, so this is ringing. Who wants to give me a period and a frequency? Oh, okay. I like the power of the -1. Okay. And from what I said before, you know enough not to give me any more decimals. I love that. Thank you. I love you guys. 2.9. That's the best we can hope for. It would be fine if you said 3 hertz. If you said 2.94, I would be a little angry. So, period 033, okay, I can accept it because it's basically the definition of 1/3. And it's 2 significant digits, but you wouldn't give any more than those. So 3 hertz, what does that mean? Hertz is 1/2, right? So I love that somebody gave 1/2 instead of hertz. It forces us to think. It's actually something over second. It can be, in this case, it is what? We can think of the wave doing something 1, 2, 3 times, right, in 1 second. If it had a higher frequency, it could do, let's say, 1, 2, 3, 4, 10 times in 1 second, 10 circles, 10 zero crossings, or whatever you want to call them. Rate, okay, yeah, it's a kind of rate, exactly. For example, you can have a circular frequency where you have radians, right, over second. So we solved this, and we're gonna see for the first time now what we're trying to compute. What does it look like? And the only way to show you is to show you the whole thing and show you what it is that you computed. You guys computed this thing here, right? So 2.9. And this is the fundamental frequency. But we said that these waves keep coming and going, and they're going to be interacting with each other, causing amplifications at other frequencies too. These frequencies will all be higher than the frequencies that we computed. So this interface here, the thickness and the velocity of the layer, has given us the fundamental frequency. And from now on, we can just do it blindfolded, because we know that there's this very simple thing, and I think you will probably have seen it in your dynamics courses as well. You just go for all the, for what do you call the numbers? Odd numbers. 3, 5, 7, 9, 11, etc. 2 times n plus 1. If you have n equals to 0, then it's your fundamental frequency. Hence the F0, right? The little index. F1 is going to be what? 3 times 1 plus, okay, 3 times your F0. Then 5, etc. So based on this, you can already easily compute what are the higher modes, as we call them, right? And the higher modes, just so you sort it out with our little plot here, they're going to correspond to bits and pieces within this soil layer. They're going to correspond to smaller depths. Because what? Because at the smaller depth, it's going to cover it faster rather than the bigger depth. But it's not going to correspond to anything within this layer. So we're seeing the finer details of the behavior of this top layer. Now, I won't make you use your calculators for that, but I can just, we can just all do it in our heads, that if F0 is 3, the next one is going to be 9, the next one is going to be 15, etc. This gives you already a very interesting idea. I don't know if any of you thought of it. if the F0 was 1, then within the first 10 hertz, and we very often only care about the first 10 hertz, we would have what? 1, 3, 5, 7, 9. But for this, we have 3, 9, and then the rest are such high frequency that we kind of don't care about them so much anymore. Even in your structures, you very rarely look at something more than 10 or 20 hertz, I believe. So where you plant this first frequency tells you a lot about how many of these reverberations you're going to get within the frequency range of interest for most buildings. And in my knowledge, we usually look at, let's say, 0.1 hertz, so 10 seconds tops, to maybe 10 hertz or 0.1 second. So these two orders of magnitude. If your first resonant frequency is very high, then maybe it's 6, 7, 8. You won't really care about the higher ones. You're going to find them at what, 20, 25, 30? They're not going to affect a regular building so much. But the first one is. So you can always keep in mind this spacing, because it helps you understand how many, let's say, dangerous frequencies do we get concentrated within this limited range that we care about. Let's say 1 second to 10 seconds to 10 hertz. Now there's one more calc that can easily be done, and this is on the y-axis. Already, if I gave you these two formulae, this one, F0, and this one for the higher modes, you could already draw vertical lines exactly where you should. So meeting the x-axis and giving me the frequency range. Now let's try and get the y-axis, and we can only do this with pencil and paper for the resonant frequency. And we call it the A0 because it's the amplification at F0. So we can compute this easily. And we'll see a couple of things about it. So, have you all realized what is this plot that we're trying to slowly assemble? I gave a hint. I said that we're going to compute amplification on the y-axis, and you know that the x-axis is frequency. So what we're trying to do is we're trying to compute very roughly, but nicely by hand, the amplification or transfer function, which is another more scary name for it. So we're doing the amplification or transfer function that describes this soil layer. So this profile. If I were building on top of this, I already know from these calcs that my structure would suffer much stronger shaking at 3 hertz, and then again at 9, 15, and then I wouldn't care so much. There's various reasons I wouldn't care so much. But the 3 hertz would be strong amplification, and it would be something I would not be forgiven, to ignore. If I had paid for this study and I knew what was the substructure of the soil, okay, because it's not the same as having rock. So this little function here starts at 0. I'll tell you this now without having shown you any numbers on the y-axis. We start at 0. Sorry, 1, 1, 1, 1, 1, 1, 1. The log is 0. 1, 1, 1, 1. So it's just a straight line if I never have the top layer of soil. If I were looking at the transfer function just for rock with itself, it's 1. It doesn't change. It doesn't amplify the ground motion. But when it goes through the soil, it's like going through a kind of filter. It's going to come out with a different personality. So this here graph is basically what we get if we divide in the spectral domain what we have on top with what we had in the beginning. So it's the ratio, the spectral ratio of the personality of ground motion after it went through the soil, this filter, with respect to what it would have been had the soil never existed, if the rock came all the way to the top. So this is the ratio for the spectrum that hits my structure compared to what would hit it if the structure was built on the underlying rock. And this is saying that at 3, 9, etc. hertz, the structure is going to receive big bumps of extra energy. This is how I would like you to interpret this in the beginning. And there's these formulas here, which basically give us exactly how much is this amplification. And what I want you to remember is that this is a ratio of the properties of the rock, so the fast, what came first, divided by the soft thing, the soil. Okay, so material 2 to material 1, the way I did the notation here. Rock to soil, VS division and density division. If you don't know the density, I don't care, because they weigh roughly similar. It's going to be different to what, 10, 15%. But the velocity of soil and rock can differ by 2, 3 times, 1.5 tops. So if you divide these, and this is a crazy example, you have 2,500 divided by 350, and a little addition of 3 divided by 2, but this is again an extreme example. If you combine these, you get what we call the impedance contrast. Contrast, hence the C. The higher, the sharper, the stronger this contrast, so the harder the rock compared to the puny soil layer on top of it at this interface, the stronger the bump we have here. The stronger the amplification your structure will receive compared to what it would get if it were happily located on rock. And if you do the math here, and there's also a little z, Greek z, zeta, which is the damping of the material, which you have here, 5%. If you do the math, oh, and 2 needs to become 1, so forgive me, I did this, I corrected it here, but not here. So this is 1 divided by all of this. None of these has any units. We said units are our friends. Here there's no units because it's a ratio, so it's dimensionless. If you do this calc, you'll find what the amplification of the fundamental peak is. The second, third, fourth, etc. is going to be smaller. I don't have anything further to give you. I can't tell you how much smaller, but if you need to plot it, it's just going to be smaller. And the stronger the damping in the soil layer, so the bigger this, I'll go to the next slide now. The bigger the damping, the lower the amplification, the faster you are killing the motion. And if you want to see an example between the maximum motion here and there for 2 different dampings, and I give you a ratio of the damping with the quality factor, for those of you who know quality factors more than damping ratios, it's very simple. It's just 1 over 2 times the other, and it works both ways. Then you can see for this Q, and for a high quality, low damping, and for a low quality, high damping layer, what might be the difference? And then similar differences and stronger ones you can have as you go on and on to higher frequencies. So my goal was to finish with this little exercise, but we've hit 11:30 and I don't know what your protocol is. I don't know when your next class is, and if you want to give it 5 minutes to do your hand calcs and wrap it up, or if you need to be rushing to your next course. So I'll need to ask you that. We're basically 5 minutes late compared to my class schedule. So you can unmute and just tell me, or even talk between you, I don't care. Just give me a pointer as to what you need to do. If you have the 5 minutes, I'd like you, while you're still fresh, to do a calc.
Personally, I have next lecture in 10 minutes.
Okay, thank you, Vasily. So what I will ask you to do is I'll send you, I'll send these slides to to Dr. Van Watsikos for him to distribute. And I very much urge you, preferably today while it's still fresh, to kind of go through these very simple calcs by yourself and apply them to see what happens and try and draw the final transfer function. And then we'll do it together in the beginning of the next class. And we'll move on from there. But this is basically to tell you that your assumption up to now with PSHA is I'm collecting all of the fault, etc., seismicity rates, vulnerability, I don't know what else you've done, data, and I'm assuming rock. This is telling you that this little silly layer on top of the rock can give you up to 5 or more times amplification at special frequencies. So your building in reality will be receiving a lot more than what your PSHA imagined, and a lot more than the Eurocode 8, right? The Eurocode 8 gave us one number. Take it up at all frequencies by a little. It was smooth. It didn't do these things, right? The reverberations. If you have this 1D resonance, this is a little thing on top that basically nobody's prepared you for. So this was the basics from this lecture. I'll stop sharing. I'll thank you for sticking around, and I will really urge you to ask me any questions. I'll leave this open for a bit. If you want to text in questions, you're welcome. If you want to send them to my email, it'll be in the first page of your slides. If you want to unmute and ask me now, if you're not in a rush, I can be around for 5 minutes. So it's your pick. Ask me anything. I'll be happy to get to know you guys better. And if not, I'll be seeing you same bad time, same bad channel next week. Have a good rest of your day.